Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 2, Lesson 5 on average rate of change. Alright, average rate of change is a really critical topic in all of math, and you definitely saw it quite a bit in Algebra 1. So let's get right into it and remember what the basic idea of average rate of change is. Alright, how fast is the output changing? Functions model the relationship between an input variable and an output variable, x and y, right? In many applications, we want to know the rate at which the output variable is changing compared to a unit change in the input variable, right? So how many llamas per hour are coming into our farm, or how many, feet per second is a snail moving, things like that, right? Rates of change are extremely important in the real world. So let's take a look at exercise number 1. A social media post has the total number of views it receives recorded as a function of time in the hours since it was first posted. The data is shown in the table below. All right, so just kind of take a look at the scenario, right? We're tracking the total number of views that a social media post has had. At 0 hours there have been 0 views, but after 2 hours there are 263 total views, 5 hours 910 total views, etc., etc. So the views are a function of the time since the media post was put up. All right, let's take a look at letter A. Calculate v of 9 minus v of 2. Using proper units, explain what this answer represents. All right, well, we've kind of done one like this before, so I'd like you to pause the video right now and go ahead and answer this question. All right, well, v of 9 is equal to 2,111. V of 2 is equal to 263. So v of 9 minus v of 2 is simply going to be their difference. And I'm going to just pull out a calculator really quick to do this subtraction because I don't trust myself. 1,848. All right, let's go back in. We're going to be pulling the calculator out quite a bit in this lesson, including even in letter B. Now, what does this represent? And it represents the fact that the number of views increased by 1,848 from t equals 2 to t equals 9. All right, so just how many views did increased, right, from t equals 2 to t equals 9? Now let's take a look at the thrust of the lesson, letter B. Calculate the average rate at which the views are increasing from 2 hours to 9 hours. Use proper units in your answer. Well, we know that the number of views increased by 1,848 views, and that occurred over 7 hours, right? So the average rate of increase is going to be 1,848, and I'm going to carry my units right here, 1,848 views over 7 hours, and therefore, right, we've got that divided by 7, which is 264. So that's 264 views per hour. All right, 264 views per hour. And this makes all the sense in the world, right? We figure out how much something has increased or decreased, and we divide it by how much time has passed, and then we come up with the rate at which something is changing. So the views are changing at an average rate of 264 views per hour. All right, let's take a look at letter C. Calculate the average rate at which the views are increasing for the intervals 0 less than or equal to t less than or equal to 12 hours and 12 is less than or equal to t less than or equal to 24 hours. Give an interpretation of your answers. All right, in other words, right, we want to know how fast the views are increasing for the first 12 hours, and then how fast they're increasing for the last 12 hours. For the first 12 hours, it's very simple because the number of views at 0 is equal to 0. All right, so for the first 12 hours, literally for 0 less than or equal to t less than or equal to 12, all we need to do is take our 2,890, divide it by 12 hours, and this isn't going to come out to be a nice number, so we'll just sort of round it. But we can just do 2,890 divided by 12, and we'll say that that's maybe 241 views per hour. And now I'll use that kind of notation. Okay? Now, to figure out the rate at which it's changing for the last 12 hours, then we have to kind of go back to letter A, and we've got to find out how much the views increased from hour 12 to hour 24, and yet again divide by 12 hours. So I'd like you to pause the video right now and go ahead and do that on your own. All right, so the first thing I need to do is simply take my 3,753 and subtract out 2,890 just to figure out, how many views did we get during that period of time. So 3,753 minus 2,890. All right, and that's 863 views. So now I'm going to do 863 divided by 12. So let's divide this by 12. And we get, let's say, 72 views per hour. So that's for 12 less than or equal to t less than or equal to 24. So that's for this period and this period. Now, the problem also asks us to give an interpretation of our answers, right? And one thing that we can tell right away, right, the whole point of a rate is how fast something is changing. So what we can see is that the views are increasing at a faster rate for the first 12 hours than they are for the last 12 hours. And that's our interpretation, right? So let me go back in here, full screen, maybe extend my page a little bit. So the views are increasing faster for the first 12 hours compared to the last 12 hours. The number of views is still increasing, obviously, but it's increasing at a faster rate for the first 12 hours than the last 12 hours. And if you were, let's say, a social media, let's say, organizer, planner, engineer, whatever you want to call it, right, manager, you might think, well, okay, that's probably because after the first 12 hours, interest in the post is starting to go down, even though, it's continuing to gain views. I mean, you're not going to lose views over time, but it's continuing to gain views, right? It's gaining them at a slower rate. And that makes sense. All right. Let's keep going and come up with a formula for average rate of change. The calculations from the first exercise are examples of average rate of change. It's known as an average because the function is likely changing faster or slower within the interval. So it's a little bit hazardous to just call it a rate of change because, it's kind of like if you were driving down to New York City, let's say it was 100 miles away, and it took you 2 hours, your average rate, right, would be 50 miles per hour. But over that 2-hour span, there would probably be times when you were going 70 miles per hour, there might be other times when you're going 40 miles per hour, but your average rate would be 50 miles an hour, okay? Now, the average rate of change formula is one of the most famous formulas out there, so let's take a look at it. For the function y equals f of x, the average rate that f of x changes from x equals a to x equals b is given by f of b minus f of a divided by b minus a, which is the same as the change in y over the change in x, how much the y values have changed, divided by how much the x values have changed. Now, as an aside, if this formula looks kind of familiar to you, it should, because this is simply the formula for the slope of a line, all right? y2 minus y1 divided by x2 minus x1, the change in y divided by the change in x. And that's exactly what we were doing in our last problem, when we found the change in the number of views divided by how much time had changed, how much time had elapsed. And oftentimes when we do average rate of change problems, we're comparing how much the output has changed to a certain change in time, because that's most often the kind of rates that we're looking for. But let's do one that has nothing to do with time in exercise number 2. If f of x equals 100 minus 6x squared, then find the average rate of change over each of the following intervals. Letter A, 0 is less than or equal to x, which is less than or equal to 4. All right, so almost always when you do an average rate of change problem, you're given a domain interval. All right, so x is going from 0 to 4. The first thing I want to do is figure out what my y values are at my two endpoints. All right, so real simple. First thing I want is f of 0. That's going to be 100 minus 6 times 0 squared, and that will be 100. f of 4 will be 100 minus 6 times 4 squared, and maybe I'll just use my calculator for that. Not that I want to think about the arithmetic that much. Minus 6 times 4 squared, and that's going to be 4. Let's go back into here. So now, right, what I'm looking for always is the change in f over the change in x. I know you just came out of geometry, so those little triangle symbols look like they should just mean the triangle f. But remember, in algebra, a little triangle means the change in. So we're going to have 4 minus 100, y2 minus y1, over 4 minus 0. And I'm sorry about those 4s being a little bit repetitive there. But this output minus this output divided by this input minus this input. Our y value decreased by 96 over 4 units. So we end up having negative 96 divided by 4, and that gives me negative 24. Now, unlike our last problem where we had this beautiful kind of unit analysis we could do, here the best we can say is that from 0 to 4, y is decreasing by 24 units per 1 unit of increase in x. Right? It's not quite as satisfying because there's no physical context for it. Let's take a look at letter B, because I want to show you something kind of cool on the calculator. But let's take a look. All right, in letter B, we want the average rate of change as x goes from negative 3.5 to 2.25. Now, keep in mind, what we're really doing here is we want the function at 2.25 minus the function at negative 3.5, all divided by 2.25 minus negative 3.5. Now, we could do exactly what we did in the last problem. All right, exactly what we did, which is we could calculate the function at 2.25, calculate the function at negative 3.5, get both of those values, do the difference, and then divide by this difference. Perfectly good. Please go ahead and do that. Not a problem at all. But what I'd like to show you is a little technique on the TI Inspire. All right, so this is kind of cool. Let me X out of this. And I'm going to go back into my calculator, and what I'm going to do is I'm actually going to open up a brand new document just for a moment. It's going to make it easiest. Okay, and I'm going to add a graph. Now you might be like, well, why are you adding a graph? And it's not so much that I'm adding a graph. I want to put the function that I'm dealing with right in here. So I'm going to put in 100 minus 6x squared. And again, yeah, then the calculator graphs that parabola and all of that. That's not really the point here, all right? The cool thing is, now if I go back and I add a sheet or I add a page, all right, and I add my calculator, here's the cool thing. there's a little button right here on the calculator that says var. Okay, and you'll find this on other calculators, including the TI-83 Plus, the TI-84, etc. If I hit var, notice it actually has f of x and f1. I actually want f1. That was the function I just put in. Now just for a second, right, if I put in f1 of 4 and I just hit enter, notice it gives me 4. Maybe that wasn't the best thing to put in, but keep in mind right here, I have f of 4 equals 4. In fact, if I hit var and I choose f1 again and I put in 0, right, it gives me 100. Your calculator can actually do function notation. It can do it, right? So it knows f1 of x right now is 100 minus 6x squared because I put that in. So I can literally put this calculation into my calculator. I can put this thing right in. So watch as I do it. I'm going to put my fraction bar in. I'm going to go to var. I'm going to put f1 of 2.25 minus f1 of negative 3.5. Got to get that negative 3.5 in there. Then 2.25 minus negative 3.5. I know that looks horrible. If you really hate that, let me put it in the parentheses, just so that it's consistent with what I have up there. But literally, I'm asking my calculator, hey, I've already put f1 in for you, right? So just tell me what this difference quotient is, and it's 7.5. And again, that's exactly what we would get if we evaluated whoops, I don't know where the 0.5 there went. There we go. That's exactly what we get if we evaluated f of 2.25, f of negative 3.5, etc. But it's wonderful because if you've got a formula, your calculator can kind of crank through that function notation for you. Of course, you've got to have a formula, so that's not going to work if you're working off of a table or a graph or something like that. Speaking of, let's keep going. All right, functions of time. Many times, most times really, rates of change occur in applied problems where the independent variable is time and the average rate is per unit time, per second, per minute, per hour, per year, whatever, right? The llama population is growing by 35.2 llamas per month, you know, something like that. So let's take a look at exercise number 3. The temperature of a chemical reaction in Celsius is given by the function C of t equals 95t plus 100 divided by t plus 5, where t is the number of minutes since the reaction began. Again, very important, t is time in minutes since the reaction began. A graph of the temperature for the first 20 minutes is shown. Letter A. Evaluate C of 0 without using your calculator. What does this value represent? All right, well, what I'd like you to do is actually, figure that out. Pause the video for a second, take 0, substitute it into that function, and come up with what the answer is. And then also answer, what does this value represent? All right, well, let's do it. So C of 0 is going to be 95 times 0 plus 100 divided by 0 plus 5. 95 times 0 is 0. 0 plus 100 is 100 divided by 5, and that's 20. Specifically 20 degrees C, and that is the starting temperature. And of course, you can actually see that in no other place than right down here on the graph. All right. So you could have probably been just like, 20 degrees C from the graph. But it's kind of nice to also see it from the formula. All right, let's take a look at letter B. Find the average rate that the temperature is increasing during the first 5 minutes of the reaction. All right, well, great. Now, in order to figure out the rate at which the temperature is increasing for the first 5 minutes of the reaction, what we need is C of 0, which, as we saw, was 20 degrees Celsius, but we also need C of 5, okay? And that one wouldn't be so easy to see from the graph, because if I go to 5 minutes here, I could kind of estimate it, right? It's almost 60, but not quite. So what I'd like you to do at this point is use our formula, figure out what the temperature is after 5 minutes, and then come up with the average rate that the temperature is increasing over those 5 minutes. Pause the video now. All right, well, I could certainly do what I did before and put this formula in as f of x1 and things like that. I don't think I'm going to do that. I think I'm just going to come back to here. I think I'm going to kind of clear this stuff out. I can just keep the same. Well, that didn't work. Let's try that again. Let's go to Menu, Actions, Clear History. That's what I want. All right, so I just need to figure out what this thing is equal to at 5. So I'm going to have 95 times 5 plus 1. Nothing is going right now. Let's try that again. 95 times 5, there we are, plus 100. I need to slow down. And 5 plus 5. And that's 57.5. Great. So let me go back in here. This is 57.5 degrees Celsius. So now the change in my temperature divided by change in time is going to be 37.5 degrees Celsius, right? That's how much my temperature has increased, divided by 5 minutes. And that now I have to come back out. Let's do 37.5 divided by 5. And that's 7.5. I'm liking 7.5 today as an answer. So that's 7.5 degrees Celsius per minute. The average rate that the temperature is increasing. For every minute, on average, we're gaining 7.5 degrees Celsius in this chemical reaction. Okay. Now, letter C. Find the average rate the temperature is increasing from t equals 5 to t equals 10 minutes. Well, we did half the work on this already, or at least a third of the work. We now know what the temperature is after 5 minutes. You now need to figure out what the temperature is after 10 minutes and do the same sort of calculation we did in B. Pause the video now and see if you can come up with the average rate of change from 5 to 10 minutes. All right, well, we got to go back to our calculator, and we're going to get there. I just want to write this one down again. 57.5 degrees Celsius is our temperature after 5 minutes. Let's figure out what it is after 10 minutes. So, oh, nope, that's definitely not what I wanted. All right, let's go with this. 95 times 10 plus, that is just not it. Okay, 95 plus times 10, I don't even remember what the function is, plus 100 divided by 10 plus 5. Yes, 95 times 10, sorry about the double parentheses there, they won't make any difference, and that's 70. And yeah, I could have even seen that from the graph. Okay, so we'll just kind of keep it this way. So C of 10 is 70 degrees Celsius. So now I want the change in temperature over the change in time, which will be 70 minus 57.5, all divided by 5 minutes. So let's figure out what that is. Hopefully I'll have an easier time here. Every time it's not going in there. 70 minus 57.5, all divided by 5, is 2.5. 2.5 degrees Celsius per minute. Okay, so for the first 5 minutes, the average rate of change is 7.5 degrees Celsius per minute. And for the second 5 minutes, from 5 to 10 minutes, 2.5 degrees Celsius per minute there. Okay, let's take a look at letter D. Your rate in C should have been less than that in B. How is this fact represented on the graph? Well, think about that for a second, all right? And pause the video now and see if you can answer anything in terms of how those two rates, the fact that for the first 5 minutes it was increasing at 7.5 degrees Celsius per minute, and for the next 5 minutes it was increasing at 2.5 degrees Celsius per minute. How is that represented on this graph? Pause the video now and see if you can answer that. Well, one of the keys to really understanding this is that the calculation for average rate of change is actually the calculation of a slope of a line. Specifically, right, if I just kind of tap on here, if I take the point at 0, 20 and the point at 5, whatever it was, 57.5, yeah, and at 5 and 57.5, I have that particular line, right? If I then connect the point at 5, 57.5 with 10, 70, I get that line. And the plain fact is, right, this line is much steeper than that one, right? And that a steeper line is indicating a line that increases more rapidly than this line. So specifically, the slope from t equals 0 to t equals 5 is much greater than the slope from t equals 5 to t equals 10. The average rate of change is always giving the slope of a line that connects the points that you're trying to find the average rate of change between. So you can always get a sense for why one average rate of change is greater than the other by simply sort of drawing in the lines whose slopes you're really calculating here. All right, let's take a look at one last problem. Rate of change as direction. Average rates of change will be positive when the function increases over an interval and negative when the function decreases over an interval. All right, so far we've only been looking at average rate of change in terms of increasing quantities, okay? And that's where it often occurs. But sometimes we also have quantities that decrease, and in that case the average rate of change will be negative. So let's take a look at that in exercise number 4. The height of an object above the ground in feet is given as a function of time in seconds by the function h of t equals negative 16t squared plus 112t plus 10. Letter A, find the average rate of change from t equals 2 to t equals 4 seconds. Interpret your answer. Fantastic. All right, so what I'd like you to do is pause the video now, figure out what the height is after 2 seconds, what the height is after 4 seconds, find the change in height, change in time, do the division, and then try to give an interpretation of your answer. Pause the video now and go ahead and do that. Well, I'm happy now that I have to deal with my calculator again that I'm not dealing with any fractions, at least not right away when I'm calculating these function values. That was not going well for me, as I think you could all see. Let's clear out the history here, and let's do it. I need h of 2, so let's do negative 16 times 2 squared plus 112 times 2 plus 10, right? So that's going to be my height at 2, which is 170. And that's 170 feet. Let's figure out my height at 4. All right, so we have negative 16 times 4 squared plus 112 times 4 plus 10, and that's going to be 202. So now I want my change in height divided by my change in time. That's going to be, 202. Let's put some feet here. Minus 170 divided by 4 minus 2. All right. So that will be 202. Of course, now you work minus 170 divided by 2, and that's 16. All right, 16 specifically feet per second. Now, how do I want to interpret this? Well, the rate is positive, all right, which means the height must be increasing. So specifically, the height is increasing at a rate of 16 feet per second. All right, easy enough. Now in letter B, what we want to do is find the average rate of change from t equals 3 to t equals 7 seconds. Interpret your answer. Awesome. So what I'd like you to do is pause the video now. Let me go back into full view mode. And use the function again. Figure out what the height is at 3 seconds, what the height is at 7 seconds. Find the difference. Divide by the 4 seconds that have elapsed. And then also give an interpretation. Pause the video now. All right, let's do it again. Popping out of here. Go over here. Let's figure out what our height is at 3 seconds. Let's do negative 16 times 3 squared plus 112 times 3 plus 10. All right, so our height at 3 is also 202 feet. Interesting, interesting, interesting. All right, let's figure out now our height at 7 seconds. Plus 112 times 7 plus 10. And our height at 7 seconds, whoops, that went away very fast, is equal to 10 feet. Now, by the way, notice right away, our height at 7 seconds is much smaller than our height at 3 seconds. So the height has decreased from 3 seconds to 7 seconds. So now our change in height over change in time is 10 feet minus 202 feet, all divided by 7 minus 3 seconds. So let's now throw that in. We've got 10 minus 202, all divided by, why not? I'll do 7 minus 3, and that's negative 48 feet per second. And let's do an interpretation on that. Extend the page so I have a little bit of room. Bye-bye hypercube. So now I can say the height is decreasing at a rate of 48 feet per second. All right. And I wouldn't want to say that the height is decreasing at a rate of negative 48 feet per second, because that would be kind of like a double negative, right? The negative specifically tells me that the height is decreasing there, and because this is positive, it tells me that the height is increasing over that interval, all right? So average rates of change can indicate both increasing and decreasing, as well as how fast. So average rate of change, exceptionally important, especially for those of you that are going to move on to pre-calculus and calculus, which are often sort of like dedicated to and focus on how fast things are changing. What are the rates of change? How much does change accumulate? Things like that. And average rate of change is sort of the basis of all of it, right? It's simply the slope formula, the change in the output over a given domain interval. So it's the change in the outputs divided by the change in the inputs, which will always result, especially in applied problems, with some kind of rate units, something per something, and most often it's the change in something per unit time, the change in something per second, per minute, per hour, per month, per year, etc. All right, you'll see average rate of change pop up here and there throughout this course. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.